The last class, we covered preventive maintenance 1 that must be performed whenever frequency deviations are detected in order to restore the interface and coupling. In addition, we learned which procedures, cares, and tools are adequate for performing maintenance. In this class, we will discuss preventive maintenance 2. Now the aim is to identify and treat the defective elements that are still not working properly even after the preventive maintenance 1. Shall we start? We should perform preventive maintenance 2 only when preventive maintenance 1 was not enough to restore the good performance of the stack. Sometimes, even after doing all procedures from the previous classes, the acoustic stack continues to fail. When it happens, we must go deeper into the maintenance. Once coupling is not responsible for the failure, one or more of the elements are defective. Preventive maintenance 2 starts with the identification of the defective element. The first step is to test the converter alone using TRZ analyzer. For this, we connect the red alligator clip to the positive pole of the transducer and the black clip to the negative or housing. Then, selecting the software the operating frequency of the machine followed by the letter C in brackets. This means that the converter is alone, only letter C. Finally, press the play button to measure. There are many different types of ultrasonic converters, so there are no absolute criteria for determining whether or not the converter is defective. The shortest way is to follow the manufacturer's instructions and tolerances. However, some basic and general criteria can be applied so that the converter's performance is minimally satisfactory. The first criterion is the quality factor QM, reported by the TRZ analyzer. For the converter alone, it must be greater than or equal to 250. To explain this in a simple way, QM is the number of times that tested element vibrates by itself by inertia after turning off the generator. Therefore, the higher the QM, the more easily and efficiently the stack vibrates. The second criterion is related to the resonance and anti-resonance frequencies of the converter, and also with the nominal operating frequency of the machine. The interval between FR and FA must contain the nominal frequency of the machine. For example, the converter analyzed with the TRZ in this figure operates on a 20 kHz machine. Note from the measurement that the 20 kHz frequency value is within the range between FR and FA, highlighted in blue. So, this converter has passed the frequency criterion. If it has a QM greater than 250, it has the minimum requirements for a reasonable performance. This is the screen of the TRZ analyzer. You will see the QM value easily right here in the corner. This other converter does not meet the criteria, as the range between its FR resonance frequency and its FA anti-resonance frequency does not contain 20 kHz, which is the nominal frequency. This converter has any defect that causes its frequency to be above the maximum acceptable value and must be refurbished. So, in short, the basic evaluation criteria for converters analyzed with TRZ are: 1. Must have a QM greater than 250. 2. The nominal frequency must be between FR and FA. Be aware that these criteria are basic. If they are not met, the converter certainly will not work well. However, they may be not enough. Met this criteria is a necessary but not sufficient condition. We must follow the manufacturer's criteria when available. If the supplier does not indicate the ranges and tolerance, we recommend the study and creation of more refined criteria by the user. Let me highlight that even when identifying that the converter is defective, we must also test the other elements, which may be damaged as well. For testing the other elements, it's necessary to use a reference converter. It might be a converter that is working properly and passed the basic TRZ criteria, but a new converter is the ideal. The booster test procedure is similar to the one used with the converter. First, we need to couple the booster on the converter with controlled torque and with clean and smooth interfaces, just as we did in Preventive 1. Then, just connect the alligator clips in the same places as the converter test. The acceptance criteria of the converter plus booster is related to the frequency of the converter alone. That's why we need to turn on the software memory function to compare the curves. After that, we need to change the software from C to C plus B, because we are testing converter plus booster. Finally, we click on play button to measure. The first basic criterion for the booster is QM greater than 700. To evaluate the frequency, it's necessary to compare the converter alone curve with the C plus B curve. The booster is approved by the frequency criterion when the range from FR to FA of the assembly C plus B is within the range from FR to FA of the converter alone. In this image, we have the range of C plus B highlighted in red within the blue one, which is the converter alone range. So this booster passes in the frequency criterion. In this other image, the booster is failing because the red range, C plus B range, is out of the blue one. It's worth stressing again that even if the converter had failed, we should still test the booster. And even if the booster fails, we still need to test the horn or sonothrode. To test the horn, the procedure is again similar to the converter test. First, assemble the complete stack and connect the converter to the TRZ clips. Remember, the converter and booster must be in good condition to test the horn. Select C plus B plus H in the software. Finally, press play button to perform the measurement. The difference between this test and the converter test evaluation lies in the basic criteria. The QM value must be 1000 or more. And for frequency, the criterion is applied only in FA. The measured FA must be at most the nominal frequency plus 0.25%, and at least the nominal minus 0.25%. In the example, we have a 30 kHz stack. The minimal FA that can still be accepted is 30 minus 0.25% of 30 kHz. So the minimum tolerance is 29,930 Hz or 29.93 kHz. Likewise, the maximum FA will be 30,070 Hz or 30.07 kHz. The frequency criterion is the same as for predictive maintenance in Class 1 of this module, the Class 4 of the course. It is worth remembering here that these criteria are basic and the manufacturer's tolerance must be respected. Furthermore, we recommend that the user of TRZ customize its criteria according to new elements' average values. In the examples, we have an approved stack and a failed one. Once the converter and booster are surely in good condition, the stack that failed has a damaged horn. This is how the acoustic stack elements diagnosis works. And this is the summary of the 3 tests to determine the defective element and the basic criteria for each test. Excellent! We already know how to identify which elements of the acoustic stack are harming its functioning. But now what? What can we do to work on the problem? Well, we saw that the problem could be in the horn, in the booster, or in the converter. For each of them, we can follow certain procedures to restore the stack. One typical defect of the horn or sonotrode is the frequency deviation. It is expected that any sonotrode increases its frequency as it gets worn, because the normal wear shortens the horn, which in turn increases the frequency. Cracks are also a common problem with horns. They are caused by fatigue and accelerated by the high temperature, so monitoring the temperature is advisable. As a rule of thumb, if you can't handle holding the part because it's too hot, a fatigue crack will soon occur. If everything is okay regarding fatigue and temperature, but we are still having cracks, there is probably some stress or concentration of mechanical tension at the crack region. In regard to frequency deviation, it is possible to work around the problem. If we determine in the test steps of the previous process that the horn has a frequency higher than the maximum tolerance, we should remove the material by machining it, increasing the slots or moving the radials forward to decrease the frequency. On the other hand, shorten the horn increases its frequency. It's important to emphasize that used horns with low frequencies are not expected, and it often indicates some efficiency problem as cracks or fatigue. Another observation is that retuning procedures can be performed a limited number of turns, as horn dimensional alterations reduce the gain and decrease its performance. Finally, if the horn has any cracks and/or low quality factor, it must be replaced. Here we can see the tuning process of a horn in progress. The horn was manufactured a little longer than the reference or project. Then it was tuned by shortening it up to reach the nominal frequency. Each curve in the graph belongs to the same sonotrode, but with shorter and shorter lengths. Besides manufacturing with the same geometry and dimensions, we must also use the suitable material and take care about some details. Otherwise, the horn simply will not work or will work for a short period of time. You can find more details about horn tuning at our webpage. Find the link below. For a booster, if the QM is lower than the tolerance, a possible approach is to disassemble the ring and check if the O-rings inside the metal ring are okay. If they are degraded, it can affect another region, which is the clamping point of the stack, as we discussed in the fundamentals module. In that case, we must replace these O-rings. Basically, this is the only possible restoring procedure. Because if the problem is tuning, it's necessary to change the booster dimensions to correct the frequency deviation. Changing the dimensions had the adverse effect of changing the gain of the stack and even may affect the nodal position, decreasing its performance even though it's tuned. If the booster is without tuning, it's best to replace it. Furthermore, if the booster is cracked, it must be replaced anyway. Summing up, if the problem is not the rings, replace the booster. Finally, if the problem is in the converter, we need to either replace or refurbish it. The typical problems of the converter are out of tune, cracked or breaked piezoceramics, crack in metallical masses, stud or thread breakage or deformation, and also breakage of metallical cables or electrodes. To refurbish the converter, we must check whether the ceramics are intact or cracked using the TRZ piezo holder accessory. If there are cracked ceramics, replace them. Clean the metal parts and restore their interfaces as in preventive maintenance. Restore the electrodes. Then, reassemble the converter with controlled pre-stress. We should use the piezo clamping test equipment for pre-stress control. In addition to replacing cracked ceramics, we also replace cracked metallical masses. There is a specific training that deals exclusively with the assembly and refurbishing of ultrasonic converters, Contact us at the email address below for more information. After refurbishing, it's necessary to test the converter using TRZ, as we have already learned. Summing up the entire maintenance module in flowchart form. Let's start with monitoring and questioning. Is the stack okay? Is its frequency and quality factor in accordance with the basic criteria? If so, everything should be working. If not, we should disassemble, restore the element's interface, and reassemble it with controlled torque. Was that enough to restore the stack? If yes, it should be working properly within the tolerance. This cycle is preventive maintenance 1, shown in the last class. It must be performed with care and procedures described there. However, if preventive maintenance 1 was not enough, we need to identify the defective element and restore or replace it according to what we saw in this class. This is the preventive maintenance 2, the last procedure of this course. At the end of this whole process, the stack should be working again. This is the last class of the Ultrasonic Welding Systems Maintenance and Getting Started course. If you have any questions, let me know in the comment section below or simply email me. I will be glad to help you. I also truly hope that this course have helped you. Be safe and see you soon.